one of the things that I reflect on occasionally is that as I go through life, I've kind of come to the conclusion that the conventional wisdom is frequently wrong, and even though it's widely held. And I'm up to about 85% now in judging that the conventional wisdom is wrong. So when I come to an event like this, especially kind of what I'll call the fundamentals, this is, if you've actually built control panels, fired them up, done the programming and the graphics, you probably shouldn't be in this class or this session. Then again, if you are one of the usual suspects in the controls industry, maybe this would be the best class for you to be in. So, some years ago I was given a presentation at a PG&E event, Pacific Gas and Electric, largest investor-owned utility in the country, and we were talking about central chiller plants, and one of the PG&E people said, well, what do you think are the best chillers? I said, yeah. I said, chillers are not important in chiller plants. What's important is how you stitch the system together and how you operate it. Well, here's the thing. What's the least important part of a control system? It's the controls themselves. And, Siemens, Johnson, Honeywell, Delta, Reliable, Allerton, they're all tinker toys. They're all pieces and parts. Most of them will talk to BACnet. Some are a little better than others. If I can give you one suggestion on control hardware, try to do a little homework on the compatibility, the BACnet interoperability of the control system. All brands are not created equal. But we're trying to make buildings work differently. And one of the things that drives me crazy, for example, I've done a lot of work in hospitals. Hospitals are like big battleships, but they're not moving through the water. They're landlocked, but they operate 24/7, 365. And I keep recalling control vendors, and I apologize to the control vendors in the room, but that's too bad. They will tout that, we correct our control valve position 60 times a second. I'm like, okay, I can't feel the change in temperature quite that quickly. And, if you're constantly moving that valve around, you're going to wear it out. The hospitals I've done, I check the supply air temperature every 5 minutes, and then I move the valve a little bit. Now, if you're doing a laboratory or something like that, an FDA lab or something like that, you're going to have to move more quickly than that. But most of our applications are just simple comfort. You don't need something that moves really fast. Most of the times, it will get you in trouble. So the biggest problem that I've experienced, and if I can impart some wisdom, this will be it, is that in the problems I see in control projects is that the controls guys understand their controls really well, but they very often do not understand the systems they are controlling. They don't understand the mechanics, they don't understand the hydronics, they don't understand the thermodynamics. And that takes us down the garden path frequently. So, what is important? In my opinion, what's important is the operational principles of the systems that we're controlling. And we generally call that a sequence of control or a sequence of operations. If you're doing controls, it's important for you to understand that. If you're directing your controls vendor, it's even more important. Because if you're going to do the commissioning, you want to see the system function and accomplish the goals that you set out for that system. And I'll give you a couple of examples. This session maybe run a little quicker than most. And my goal is to just kind of plant a seed in your head, in your brain about what's really important about controls. It's not bells and whistles. It's does it get the job done? Recently was working on a Federal Aviation Administration facility. It was an Air Route Traffic Control Center. They call those ARTCCs, A-R-T-C-C. And this one covered a coastal area and all the way across an ocean. It was a very important facility. Not sure that the guys that designed the facility in the first place were really all that sharp. And they had oversized condenser water pumps because they not only had to take the heat out of the chillers, they occasionally had to take heat away from the emergency generators that they operated. And even with only a single chiller online, they had 2 cooling towers dispatched. The cooling towers each had 2-speed fans. And the sequence that they set up was to have Tower 1 fan come on low, then go on high. If the condenser water continued to warm up, then they started the second tower fan, the fan on the second tower at low speed, and brought it up to high. Well, with only 1 chiller online and having a whole lot of flow, that's why they had to have 2 cooling towers. The water going through the 1 cooling tower now is not being cooled at all. So the other tower now is trying to compensate for that. And what we ended up with was that the fan on Tower 1 ended up being on high speed all the time, even though there wasn't enough load to really require 1 cooling tower. It was beating itself to pieces trying to maintain a condenser water temperature, and all this other flow is going through a machine that's not working and basically defeating its purpose in life. So a better sequence, and this was a constant flow system, was to bring tower fan 1 on low, then go to tower 2 and bring its fan up to low speed. Now, if you're looking at like a 2-winding motor, your low speed is half. Rough and dirty, a cooling tower that's pushing half its airflow through, it's going to provide about half its capacity. Well, now we've got 2 fans at half speed. If you know the fan affinity laws, that means we're at about 12.5% power, rough and dirty. So we're getting a 1 whole cooling tower worth of heat rejection with only half the total power of 1 motor. Now, in fact, we only had 1 chiller online. It wasn't fully loaded, and roughly the tower and the chillers were equal size. What would actually happen in this scenario is the lead tower would come on low, and the lag tower would cycle on and off at low speed. But even if it was running constantly, we're only using half the power. Most of my chiller plant retrofit projects, I've mixed and matched cooling towers with the chillers. Cooling towers are cheap. And even though the manufacturers will tell you can only reduce the flow a certain amount, very often you can reduce it a whole lot and have it still work properly. And the only way to know on a given tower is to test it in the field. That's the best way to find out. We did that at Cal Poly SLO about a year and a half ago, and the chief engineer had never considered the possibility of dispatching 2 cooling towers with 1 chiller online and running the pumps at the fans at low speed. He didn't think it would work. So we went out, flipped a couple of valves at the head end of the building automation system, ran the water flow through, half water flow through 2 towers, and they worked fine. The fill was completely wet. We didn't have any problems at all running the towers at half water flow. Half water flow. Even better than just changing the sequence was to put a VFD on the oversized condenser water pump and close off the other tower, only run 1 tower. And curiously enough, when we did this in front of the owner, what he discovered was that the load was low enough, he only ended up with his 1 tower that was online running at low speed. Previously, it was sitting there running at full speed, and it was really struggling to keep up. He was really surprised. He didn't think that that would happen. Here's my second example. John, where are we on time on my presentation?
You have 12 minutes.
Very good, very good. Fan tracking. In this particular example, the control contractor, the vendor, decided he would ignore the sequence that we gave him for tracking a supply fan and a return/exhaust fan. And because the air handling unit that was provided had these flow measuring pitot grids at the inlets to the fan, being the controls guy that he was, well, I'm going to measure airflow directly, and I'm going to maintain a differential of airflow between the two fans. Now, he had a little problem. He was trying to put this thing online, and he hadn't yet got his outside air damper operational. And it was a high-quality air handler. When that damper was closed, it didn't leak. So here's what happens. No outside air. The airflow coming in the return, going through the return fan, going through the coils, going through the supply fan, it's the same airflow. It can't be anything but the same airflow. So what happens? The control system is trying then to slow the return exhaust fan to maintain a differential, but it can't do that. Next thing you know, the static pressure sensor out in the ductwork says, I don't have enough static. I better speed up the supply fan. And it sped the supply fan up. Now the return fan says, I need to slow down even more. Pretty soon we had the return exhaust fan at 0 speed, and it was freewheeling going backwards because the supply fan was sucking air through it. And it wasn't a problem until the fan tried to start again, the return fan, and the VFD, because it's trying to overcome this inertia going the wrong way, took itself offline, and control guy decided that the electrical design was bad, that the VFD was faulty. He didn't understand that, the physics of the air handling system, and no matter how much you tried to slow down that return fan, the air going through both machines was going to be exactly the same. It couldn't be anything else. That was really fundamental. He should have understood that. Now, the control sequence that he was given was to simply use a speed differential. Supply fans at 50 hertz, we run the return fan at 45 hertz. And I have used this particular control sequence, which is dirt road simple. You don't need any airflow measuring devices. Oh, I got 50 hertz here. Let's see, what am I going to do? Oh, 45 hertz, okay. And you can dial it in. In fact, as the speed goes up and down, the total airflow in the building goes up and down, you can adjust that bias. I just balanced out a hospital wing, a patient room wing, med surg, and we basically put the air handling system into 2 modes of operation. Full airflow when the sun was shining, because patient rooms all have a lot of glass, typically. They're designed for 8, 10, 12 air changes an hour. Code in California, for example, says we only have to maintain 4 air changes an hour, 2 of which have to be outside air. So we were able to go from 10 air changes an hour down to 5 and still be well above code at night when we didn't have a solar load. Curiously enough, when we were running at full airflow, we actually had to run the return fan a little faster than the supply fan in order to have the building be at about 0.02 inches of water static pressure in the building. Now stop and think about that. 0.02 inches. That's a shallow puddle of water on a tabletop. That's hardly any pressure at all. When we went to our low flow operation though, it was curious. We had to actually end up slowing the return fan down and making it run slower than the supply fan in order to maintain our 0.02 that we had. So this whole thing about doing controls, what's important is understanding what you're trying to accomplish. Here's the moral of the story. Tinker toys are not important. They're universally available. Sequence of control, understanding how the systems and equipment actually work, that's what's important. That's the key. And that's the end of whatever I'm going to provide you in a presentation today. But